Well, I think that we should start. Okay, I see we have 3 people online today. All right, so I wanted to begin with this slide because I have a couple of points to make, okay? We're all aware now that lithium, of course, is the go-to metal for batteries. And the reason is, of course, it's lightweight. And because of that, it has a very high energy density on the order of 3,900 milliamp hours per gram. Okay. And over the weekend, I decided I would learn a few things. So you can now buy a cell phone, and the cell phone might be rated at 4,000 milliamp hours. And that means if you ran it at 1 milliamp, you could use it for 4,000 hours. But in fact, we usually use our cell phones at about 400 to 500 milliamps per hour, which is why a battery lasts about 8 to 9 hours, okay? So that's kind of interesting. So I also learned that a typical cell phone has all of 1 gram of lithium in it, okay? So in principle, it's a reason for it lasting about 4,000 hours or having a capacity of 4,000 milliamps. Okay, so the point with talking about that is then I want to go to, not this slide, but this slide, because you can see that silicon has a capacity of approximately 3,600 milliamp hours per gram. And as we've been learning, silicon is the next one of the holy grails in anode materials. Why? Because unlike lithium, it's available almost everywhere, okay? So that's one of the reasons, the drivers, even though, of course, it has this incredible volume expansion of up to 400%. So I just wanted to make that point now, but I'm going to switch gears because everybody is here attending online or in class. And I want to make a comment about homework, okay? Every time I give a homework the first time in class, everybody gets total credit, 100%, no matter what you did, because you have no idea what my expectations are. And so this is a sort of a training exercise to challenge you to understand what I want, such that you can do a better job, Reed's professional job, or more professional job next time, okay? So having said that, given that I sent the homework back yesterday and I had made Wednesday as the next due date, I would be happy to extend the due date to Friday to give you enough time, because it's important for you to be more sophisticated where necessary. Not everybody is. So I am going to just let you turn it in Friday morning. Okay, anybody got any issues with that? Let me see over here with the chats. Nope. Okay, so keep that in mind. This is a basic course, and there are various levels of experience in the class. And so I understand that some of you will have much less experience than others, and this is partly why I'm setting the tone and the information in the lecture a little bit lower than some of you would appreciate, because of course I'm trying to bring everybody up to speed, okay? And sometimes that even means me, okay? So having said that, I want to proceed with an understanding of what we have here. And so I just want to rehash this set of slides because, in fact, because of silicon's problems, of volume expansion. In this slide, we mixed silicon in the form of a nanoparticle with graphene, which is basically a layered carbon, but in nano-sized particles. And we see that when it lithiates the first time, almost all of the crystalline materials disappear in the X-ray powder diffraction pattern, okay? Part of the reason for this is that the particles get so small that the number of crystalline planes that interact with the X-rays is much less, and the ordering of those planes is distorted by the change in size, and so you start to see much less, or you see over here something that's very broadened. That's a consequence of having very small particles, okay? So that's just a point to familiarize you with things. I want to also mention something else. I'm going to talk about subject matter that I will not immerse you in completely because we will return to it. So this is a constant theme in this class, that we're getting you familiar with concepts, and we will eventually build up your background knowledge to the point where you can understand and feel comfortable with more details. So keep that in mind. I am not being cursory in my presentation because I think it's not worth the effort. Everything is worth the effort, but it needs to be done so that everybody is carefully brought up to speed, okay? So one of the things that I mentioned, one of the things I realized over the weekend was that we are going to talk about charging and discharging, and there's certain rates that people use to charge and discharge batteries at. So common rate is 1C, okay? 1C is 1 charge, okay? And that rate is a discharge of an entire battery in 1 hour, okay? So a battery with a capacity of 100 amp hours should produce 100 amps in an hour, okay? And a 5C rate would be 500 amps, but you couldn't get 500 amps out of a 100 amp hour battery in an hour, okay? You could only get 1/5 of an hour to get that out, okay? And the CO2 rate would be 50 amps, all right? So you do it in 2 hours, all right? And C is generally capacity divided by 1 hour. All right, so a rate of C over 20 would be a discharge, a full discharge in 20 hours, and you could also charge in that time, okay? So C over 20 would also be 0.05 C. Again, you'll see examples of this, and there are several reasons for using charge and discharge rates. Some of them are a consequence of what kind of application you're looking at. Are you going to need a lot of energy in a short time? Or are you going to need something that lights an LED forever? Okay, and LEDs take very little energy. And that's why you don't need a very big battery. My bicycle light that I use front and back, if I go 4 hours of bicycling, it uses up the charge and I have to recharge it. And my onboard GPS also lasts about 4 hours. So every time I get off my bike, I recharge them. All right, but it's great because I can just plug them in to a USB port. Okay, so now there's something else that needs to be said at this point. You will see people charge initially at very slow rates. So why is it that people would charge at very slow rates? What happens the first time you charge? Catherine? Yep. Let me just see if I have another chat here. Okay, no issues at all, okay. Yeah, it's to form an SCI, so solid electrolyte interface. Why is it important? Well, in the homework, you saw that the solid electrolyte interface should be stable. If you form it slowly, you can envision that it would be dense and it would be something that would be relatively defect-free because you're applying a small potential, and typically where you have pores, the potential is higher there because it's concentrated. So that's the first place that a new reaction would happen. So the pores get filled, all right? And so you can see that a slow uniform charge or discharge will lead to a dense and uniform SEI. If you do it really fast, you can envision, for example, that the pore gets closed over without getting filled, and then you get a defective SEI, which leads to potential for failure later on. Okay, so that's why we'll see slow charge rates. Why do you have fast discharge rates? We're going to see some rates where you go up to 5 and 8C, all right? So 8C is 1/8 of an hour to discharge an entire cell. Why would you want to do that? Might be for an emergency, okay? It might be that there's some requirements. All right, so just for amusement, how many people have heard of the plaid mode for Tesla? Okay, so how many people have heard of the movie Spaceballs? All right, so I have not seen the movie, but I'm told that the Spaceballs is sort of an amusing story about astronauts in rocket ships that when they go really fast, the outside universe turns plaid. Okay, so that's called plaid mode. So in an electric vehicle, for those of you who have had experience in them, for those of you who may get some experience, you can go really fast, really quickly. Okay, because you don't have a combustion engine that has to torque up to get the horsepower. The electric motors are instant on. So this is, when you see electric vehicles with 1,000 horsepower or 1,500 horsepower, it's a consequence of having very good electric motors only. One of my former students is ordered a Porsche electric vehicle. And he claims that it's now arrived. He lives in Baltimore. He's working at one of the satellite companies. And he claims that once he gets it, he's going to drive it out here. So I've suggested that he could give you all a ride in it. We'll see what happens. Okay. So having said that, all of these are things that are not, well, the plaid speed, super ridiculous. Oh, I think there's another one that's called ludicrous. That's the one before plaid, exceptionally fast. So those are where you have a huge demand on the battery. Obviously, you're going to waste the charge and it's going to dissipate what you're able to use for long distance, but nonetheless, who cares if you're going to get to go fast? So these are things that are changing society. In fact, EV racing is very big business. Now, I suspect it will supplant a lot of the combustion engine racing, and it will be very interesting because we're moving away from mechanics to technology. All right, so those are kinds of issues that we are going to deal with here. Okay, so now this is a charge-discharge curve for that mixture of nanosilicon and graphene, okay? And remember that I said that the capacity of silicon is 4,000 milliamp hours per gram, just under that. I was 3,600, okay? So when you see the capacity that you get, it starts way up here at 200, drops immediately to 150 as you form an SEI, okay? And it continues, okay? Now, the charge-discharge ratio should be close to 1 unless you have some sort of failure mechanism that depletes one of the other, the and this is against, I think, nickel, cobalt, aluminum. We'll learn what that is just a few slides from now. Okay, and we should be experiencing something a bit higher than this. Okay, we're now not limited by the silicon, we're gonna be limited by the nickel, the NCA, all right? So this initial discharge is C/15, okay, then C/5, all right, to the 5th to the 10th cycle, C/2 to the 10th to the 50th cycle. And this is not atypical for how to test a battery, all right, but it's very nice that you see charge and discharge match, so that this tells you the Coulombic efficiency is close to 100%. In the homework, the efficiency in this, somebody mentioned that even if you have an efficiency that's 99.5%, if you do 1,000 cycles, each time you're losing 0.5%, eventually the battery goes away. It has to be 99.99 to be really, really good. And these are issues that basically determine the aging properties of a battery, of a lithium-ion battery. Indeed, something quite interesting, which some of you may be aware of, but maybe not. A lot of the automobile batteries that are used in electric vehicles, they eventually lose their capacity to provide you with a certain distance travel. And then you can, of course it's expensive, but you can exchange them for new batteries. The batteries that are removed are not sent to be recycled. They can be used elsewhere for storage of electricity, because they are just not good for automobiles, but they're great for storing electricity at remote sites. So they have second and sometimes third lives. Okay. So again, 99.5% if you have 1,000 cycles is not the best. All right. So this is the failure mechanism that we mentioned last time. Okay. So you have silicon and graphite, graphites to conduct electrons, silicons to store lithium. All right, and then the first cycle at C/15 on the last slide, you make an SEI, okay, all right. And the problem is that as you discharge, it shrinks and you start to break up the particles of silicon, and then you repeat the charge and you build another SEI, okay, because you've cracked the first SEI. And then as you go on and on, you are getting expansion, pulverization of the silicon particles, and eventually you create cracks in the process and the battery goes bad. Okay, so this is another reason why I gave you this information about rate changes. All right, so these are the same graphite silicon monoxide cells, and they are charged against NCA, all right? And these are rates at different temperatures. Remember that in this system, there are liquid electrolytes. So 65 degrees C is really pushing the limits of a lot of liquid electrolytes, but it's fine, you should do that to test the materials. So over here is the cycling of a cell, all right? And it starts out by discharging at 4.2 and going to 1,000 to 1,200 milliamp hours per gram. And when you do it at 3C, it drops a little bit. Okay, so you go from the first cycle here, that looks pretty good, all right? But if you go to 45C, okay, then it falls off quite a bit. Let's think about this in a practical sense. If you are operating your vehicle or battery at 45 degrees, then it ages much faster than if it's operating at room temperature or ambient. Since most of the time the battery is not going to be at ambient because it's going to be hot, all right? Not really hot, we could argue warm, okay? You can touch 45. You may not like it, but you can touch it, it won't hurt you. So that's not unreasonable. So your lifetime here is not what you would like. All right. So then, of course, as you can guess, that it's rate dependent. Oh yeah, a point I wanted to make about rates. Why is it when I go to faster C rates, my capacity drops? The answer is in the homework, but anybody want to take a guess? Jeff?
Just because you're pumping more out faster?
Are you able to pump fast enough?
No.
Probably not. Okay, so if you can't pump fast enough, then the capacity is going to be less. And what is a really neat test is if you go back to the original charge discharge rate, if it returns to the original values, then you know that the higher C rate is a diffusion problem, or you could argue it's a kinetic problem. It doesn't, you can't get the lithium in and or out fast enough. Okay, so it's not necessarily bad. It is really something that you have to understand because the applications windows get smaller when you have constraints. Typically 3C is not a big constraint. You should be able to do 3C, but not always. Now, let's talk about cathodes. Okay, but in passing, one of the important things that I wanted to mention with respect to kinetics and rates of lithium ingress and egress is that LTO, lithium titanate, is got a three-dimensional structure, and you can get a lot of lithium in and a lot of lithium out, and there's no volume change. So even though it's very low voltage and its capacity is only 150 milliamp hours per gram, because it's stable, because it doesn't undergo expansion and contraction, it means that it's dimensionally stable, which suggests that the batteries made with it can have a long lifetime, okay? So these are all our anode materials. And again, the take-home lesson from this chart is that the higher the voltage difference between the anode material and the cathode material means the faster you can get electrons in and out. Not always correct, but to some extent it's giving you the opportunity. So the graphene silicon monoxide system falls in around here, okay? And the lithium ions, lithium metal is here. Silicon is the holy grail because it's cheap, but we're gonna end up finding that sulfur, lithium sulfur, is one of those things that lots of people would like to be in because sulfur is cheap, readily available, but that has its own problems. So let's, for the moment, we're going to talk about only about specific capacity and not about specific energy. We will have a lecture on key items for understanding energy storage later on, okay? So these are materials that have average voltage differences with lithium, roughly 4 volts, except for LFP, 3.5, okay? You can note that the specific capacities are all pretty much around the same. Oh, there's another point I wanted to make. All right, so something that we came up with and talked about previously is the fact that if I have a battery with if I have my cell phone battery with 4,000 milliamp hours, okay, the question is, can I use it and exhaust it to get all of the energy out? Okay, and we're going to see that frequently for batteries, we really don't want to get all the lithium out of the anode or all of the lithium out of the cathode, because when we do, we get an extreme collapse of the crystal structure, which makes it difficult to further discharge or charge. And that is something that is important. So this is also why when we saw that one slide where we had the energy gap was bigger, we only allowed for a ratio, an N to P ratio of 70%. That was because that was reproducible, and the failure, I don't know how to put it, the degradation process, the efficiency could be much worse. So one of the first materials, LCO, has got a decent specific capacity. LFP is a little bit better, okay, the 3.5 volts. And then we're going to talk about, this is NMC is now, this, even though it's labeled nickel, cobalt, manganese, people use NMC. We'll see why in a second. And NCA replaces 1/3 of the cobalt, or half in this case, with 15% mole percent just by using 5 mole percent aluminum. Okay, so the savings, and of course you increase the nickel content. We're going to see that nickel is much better in terms of high voltage, but there are problems with high voltage, which we'll see in just a little while. All right, so just to understand the crystal structures and how they play a role in charge and discharge, remember that I told you it's LTO is 3D, but it's not here, all right? So these are olivines, all right? And they have a very nice flat discharge capacity, and again, 150. Then you have NMC, not N, this is, I'm sorry. NMC is now the traditional way to label these, but this is a nice plot, okay? All right, so it shows that it goes up to 4.5 and it discharges down to 250. Again, we may not want to go all the way to full discharge, all right? So the nickel manganese spinel is up here about 4.7 volts, and it's got a relatively flat curve at this high voltage. That's why people are really interested in it. And in fact, we're working on it in my group right now. And then this is a different NMC, okay? And so you can discharge it here and you can see it falls off a lot, okay? So it falls off a lot because there's no more lithium left. No, there's some lithium left, but again, the ability to get it in and out becomes difficult. It's like it's asymptoting in terms of how much lithium will come out and how stable the lithium is in the reduced lithium content structure. Okay, so this spinel is 3D. This is layered, so the lithium goes along the layers. This is also layered. Okay, so those give you a feeling for the way lithium goes in and goes out of the structures, and that has some effect on the voltage. In addition, we're always worried about costs. So LFP was one of the earliest materials commercialized, okay? And that was one of the early discoveries of the Goodenough group in Texas. And what is something that I've alluded to a couple of times is that LFP, as it's discharged, undergoes a phase transformation, okay? So as you lose lithium, you get a lower lithium content on the surface, and a higher lithium content in the center. And of course, the lithium has to diffuse out. So the way to get the lithium out faster is simply to make the particles smaller. Okay. And so it's single phase right here, but you are building up a second phase on the outside. And the phase transformation also has differences in potential. So we're not going to talk about it right now, but the two phases do have slightly different potentials, and they do change the behavior of the cell, but we're always going to try and operate between here and here when we use a cell like this. Okay. So again, having a high voltage is very good, but it has trade-offs, some of which are quite dangerous. Right, so this is a phase diagram with manganese, cobalt, and nickel, a ternary phase diagram. And we are interested in making various compositions with the highest voltage, but the safety is the drawback here, all right? So high voltage spinel is over here on the manganese nickel tie line, all right? And then we see that we're really always interested in reducing cobalt. All right, so a lot of these are NCMs with different compositions, and we're going to talk about those in just a second. There's a lot of information there, but one of the issues and one of the driving factors is the attempt to eliminate cobalt. I don't know if any of you paid attention, but there was a gold mine collapse. I think it was in Africa, and I don't know if it was in the Congo, but 50 gold miners died in this collapse. Why? Because the people that run the mines aren't concerned with worker safety as much as they are with making money. And this is part of the issue with cobalt. So these are the typical cathode design compositions. So original lithium cobalt oxide, LCO, all right, is a little bit of lithium and the rest is cobalt. NCA is wonderful because look at how much cobalt you replace. Okay, just for adding a little bit of aluminum. NMC is the 1/3, 1/3, 1/3, right? 1 to 1 to 1, right? 6 to 2, all right? So now we have a lot more nickel, and 811 is still more nickel. And this is, now why are people doing this? Think of it this way. I can buy lithium, nickel, cobalt, and aluminum. I can control the composition, and when I control the composition, I can get now the capacities at 111 of just short of 150, a little bit more, and all the way up here to 200 milliamp hours per gram. So obviously, I always want higher capacity. And of course, I also want to avoid cobalt, and I want to do my best to make material that's stable. Well, let's do a sort of a straight across the board comparison. You know, when you go shopping, some of the websites say you can compare all of the products features. So we could kind of do that here, all right? So LFP is a very flat discharge, right? And but it has a problem with a self-discharge rate. So sitting around by itself, it undergoes self-discharge. Why is that, Catherine?
I don't know.
Is it because it can also have some good conductivity, electronic conductivity with electrons, so it leaks across the anode? Or it self-oxidizes? Anyway. Yes, they all have low electronic conductivities, you're right, but some have slightly more. And that's part of the reason for self-discharge. Okay, but yes, all very low. Okay, and China is a large producer, NMC, and we saw a very large number of flavors, all right? 811 is now an industry favorite, okay? But it has its real serious problems, okay? So now NMC is replacing LFP in a variety of applications, okay? And NCA is the best compromise because it eliminates a lot of cobalt and it has a reasonable, let's see, we're going to see this. All right, so the voltage is a single slope, which can be used directly to understand the state of charge. So when you can read the voltage of an NCA system, then you know basically how much charge is left. Okay. Of these materials, NMC is a better selection for batteries with high capacity and high power. LFP has specific energy of 90 to 120 watt hours. We're going to again come back to that, so don't worry about it. However, all of the nickel cobalt manganese systems have problems of thermal stability. Okay, so when I discharge the various materials, for example, lithium cobalt, then the initial voltage that I could get is about 4, okay, 4.4. And as I discharge it, I start to lose voltage and eventually it falls off at about 140 milliamp hours per gram, okay? And the same is true for NMC 811. It's almost out there, but it can go all the way to 200. That's desirable because the total capacity then is closer to 200. Now when I charge these, so this is the discharge curve, and when I charge these, I'm going to charge them beginning at somewhere around 3 volts. And then they're going to start to pick up lithium. And then as I continue to charge them, the voltage that I have to apply to get to full charge goes up to the same voltage that they started at, okay? So I actually have to apply a slightly larger, higher voltage to begin with. So NMC, X plus Y plus Z equals 1, 111, 532, 622. Think about the man hours that have gone into identifying these compositions. Okay, for sure, someone has been spending hours in the lab making different compositions to find the right composition, the right particle size, the right crystal structure to get these materials, okay? If we could choose based on economics alone, then lithium manganese would be a really lovely choice because it's low cost. It has a spinel structure that allows lithium to move in 3D. Okay, it has a high operating voltage of 4. Remember that for LFP 3.5 is our limit. Okay. The problem is that in liquid electrolytes, manganese 2 dissolves. Now, when you operate systems with manganese in them, then you have, during the discharge and charge, you also have formation not only of manganese, well, you can start with manganese 3, but you can, on charging, make some manganese 2, and you can also oxidize it back to manganese 3. But the problem is that the properties of, when you have manganese 2, then you have lithium that takes the place of the charge, and that means higher lithium capacity. But you have a problem with lithium dissolving out, manganese dissolving out. Manganese oxide also will oxidize organics, which means that they'll degrade. So that's why people are worried about dissolution, and there's more to this than meets the eye. Okay, so it could be mixed with NMC to get a layered structure, okay? And then the this optimizes the lithium storage, as it says here. And that's what people have been doing. So now remember I said that NCA has a uniform discharge profile. And so this is the comparison of the voltage profile, okay, and the amount of lithium in the metal oxide. As you start from, in the case of LCO and NMC, you can be up here at above 4.5, 4.7. This seems to show up to 5. I'm not sure that's really useful to know, but the important thing is, if you, just for comparison, if you look at, as you deplete the lithium and lithium nickel oxide, you see these various plateaus, meaning that you have phase transformations, which means that there are some kinetic barriers that occur with regards to the ingress and egress of lithium. In contrast, NCA has a relatively uniform profile, okay, starting from up here about 4.7. And this is why when you find the voltage of a cell, you know exactly where you are on this graph, which means you know how much lithium, how much energy you've discharged, and how much you can go further. Again, you really don't want to fully discharge most batteries. Okay. It is true at one point early on that when you had a computer, you discharged it completely the first time. Okay, I think that's changed now. I don't recall, I should have asked, but it doesn't matter. Anyway, you can also see that NMC has a nice, relatively uniform discharge profile. And that's, again, desirable. Okay, so LCO, energy density, 180, that should be watt hours per kilogram, not the weight. All right, capacity is 274. Low self-discharge, okay. Good cycling performance used in small electronics. NCA, you reduce the cobalt content as a high capacity, high operating voltage, you can see up there. Excellent rate performance, slow reaction with electrolytes. That's a problem because we don't want it to degrade. All right. So if you had a choice, you would try to eliminate cobalt and you try to eliminate nickel. But if you had to choose between cobalt and nickel, then nickel is what you would prefer to have. So we're going to end up seeing a lot of systems and talk about systems that are high nickel content. But when we start to do that, we run into issues that are, in a sense, scary, okay? So NCM, so one-third nickel, cobalt, and manganese, has a thermal runaway temperature at 155. That means that if it gets too hot, it starts to generate oxygen. And when it starts to generate oxygen, you get oxidation of organics and you can get explosions. All right, NCM 523, pretty much the same, but by the time you get to 811 or 811, it's 130 degrees. You have a 20-degree lower temperature range. This is, of course, in using against graphite with lithium chlorophosphate as the analyte. By the way, one of the things that we don't spend enough time on, but we will in this class, is the fact that an electrolyte in liquid and polymer electrolytes, you usually have a salt dissolved in the liquid. In the polymer, you can have a salt dissolved in the liquid, or the polymer itself can provide the anion And the cation would be lithium or sodium or magnesium, not likely with magnesium for reasons that we can talk about. So this means that even though 811 has higher energy density, we are interested in mitigating against the possibility of failure with explosive results. This then is why you saw in one of the earlier slides that to introduce a way to prevent thermal runaway requires that you add safety factors in many forms. Remember, one of them was a polymer separator that would melt, say it would melt at 130 degrees, and therefore you could not get electron transport or lithium transport at that temperature. Not that you'd want it, okay, especially not with liquid electrolytes. This is, of course, a continuing argument for avoiding liquids. In polymer electrolytes, they are ways to avoid the flammability of organics, but in general, the lithium ion transport is slower unless the polymer separator with the lithium in it is thinner. And this is for another lecture, okay? So these, again, reiterating what I said earlier, we are trying to familiarize you with the various aspects, and we will go into detail more in the future, okay? So don't worry about being at least a little bit confused, if not a lot confused with what I say. We're going to get this in more detail and we're going to be more structured. So everybody would love to use a lithium oxygen battery, okay? And the reason, of course, is oxygen is free in the air and the energy density uses the energy density of lithium, okay? In this case, you would envision one that uses a liquid electrolyte. Oh, wait, organic. I just mentioned liquid electrolytes and I presumed that everybody would hear organic, okay? Over here, this lithium oxygen system has water. So why would we even think about water? Because water and lithium metal are not happy together, or rather they're too happy together. Okay, and they get rather exuberant and you get explosions or fires, all right? But if you have a lithium ion conducting membrane that keeps the water out, then maybe it works. Okay, in this instance, you have a porous carbon system plus a catalyst, and you form lithium peroxide. And then when you charge it, you decompose the peroxide, releasing oxygen and getting lithium to go back the other way. Sounds ideal, right? Lithium peroxide is also a problem. All right, I don't know what background you all have, but imagine that I have carbon and I have oxygen. What do we normally think about carbon interacting with oxygen? Yeah, more than that. When you heat carbon in air, what does it do? It burns. You're right, it burns. So I can heat carbon fibers in air and they're stable to about 500 degrees centigrade. Okay, so I can use some forms of carbon in air as long as they're very dense and they're graphitic in nature, meaning they're crystalline. On the other hand, every time I expose carbon to air, I'm going to get, what did you say on the surface? Double bonds, I'm going to get carbon, oxides of carbon. So I'm not sure exactly what Of course, we want the carbon because we need electron transport, right? So you have to envision the technology that does this. Maybe I have to have a thin film of Teflon. Okay, but it turns out Teflon will also interact. So this kind of idea, and of course it's high surface area carbon. So anytime I have higher surface area anything, it burns faster, right? It reacts faster, but I need high surface area. So there's a technology gap issue here. It's the same one over here, whether I use a liquid electrolyte or not. Okay, so these are interesting thoughts, and I'm demonstrating, or I'm going through this with you because it seems to me that there's some value in talking to you about what people are trying to sell for the future and recognizing there are some issues, okay? So advantages of a lithium oxygen system are high specific energy density because it relies on lithium metal. Air is everywhere. It's disadvantages because you still have issues with lithium metal batteries. You get decomposition of the active materials because carbon reacts. The lithium could react and form something that isn't, can react with the surfaces of other things. Poor rate capacity, power output. Well, I think that it's not been optimized to the point where you can make this kind of a claim, all right? And high charging over potential. In reality, I have to apply a much higher voltage to get the lithium peroxide to decompose than I'd like. In addition, if you use any liquid electrolytes, you start to form organic oxides of organics, and therein lies a serious degradation problem, okay? So I'm not going to emphasize this in great detail because it's, as far as I'm concerned, it's outside the purview of the class. I just want you to see it. All right, so remember I said the over potential is 4 to 4.5 volts to drive the reaction back, okay? Can this over potential be mitigated with photocatalysis? All right, photocatalysis. So where do I have to be to do photocatalysis? Where? Well, where it's sunny, right? If I need to use photocatalysis, then that means I have to have very high surface area electrodes to capture sunlight. Gee, I'm not sure. I'm not sure there's anything here that is very promising, okay? Because I can't use an automobile to capture enough light to make this work. All right, now I wanted to do this, but I wanted to use this cell as a comment. I think this is premature to present this in the respect that it's coming technology. On the other hand, I also want to make sure you're aware of the fact that you need to be critical when evaluating something published, okay? Nature Communications. This means that it's one of the superior articles that's been chosen to be published by Nature magazine. All right, so this is your photoelectrode, and it's exposed to light, and it causes the promotion of an electron into an oxidizing medium. So it's a dye-sensitized titanium that gives you a hole and an electron, all right? But you need lithium, okay? And so what did I say about your cell phone and the amount of lithium that you have in it? Flora, how much lithium is in an average cell phone? Can you please speak up? 1 gram, right, okay. Now, I need a mediator, a counterion for my lithium. Electrolyte, lithium iodide, and lithium perchlorate. Does anybody know what the atomic weight of iodine is? It's 192. So if I have 1 gram of lithium in my cell phone, how many grams of iodine would I have? 200 grams. Can I fit that in a cell phone? No, this is idiotic, okay? All right, that's why it's publishable in Nature, but the people who are reviewing it aren't paying attention to the fact that this is not likely to be very practical. That's why I want you to see this, okay? People use dye-sensitized titanium for making photovoltaics. That works, okay? And that works, but not with iodine mediation. So all of these are worth only the fact that they serve as a way to illustrate being critical. Okay, so I don't even want to spend time on this because I think that I would be wasting your time. All right, so all of these are mediated charging using light. It works. This is well done for what it is. Okay. And this is a material graphitized in your slides that you had previously. This was called graphic carbon nitride. I realized on reviewing it that it can't be graphic carbon nitride because graphs we make with plotting programs, but graphene would be graphitic, all right? This kind of a structure is very unusual and very hard to make, and that's another story in and of itself for a different day, okay? Carbon nitride is, until let's say 5 years ago, was considered to be unknown. Now there's people who make carbon nitride, but it's kind of making diamond cells. Now there's some examples of something like this. All right, so these are all examples of using light. And this is more light. And this is using titanium nanorods. And titanium nanorods are okay, but if you use photolysis with titania, let me back up a bit. The reason I know something about this is because there's a lot of work that's gone on to coating windows with titania. Okay, why? Because titania absorbs UV light, creates electrons and holes, and those actually will oxidize organic coatings on the surface of windows, and when it rains, those organic coatings get washed away. So now I'm going to use titania in an organic liquid, and I'm going to photolyze it. Guess what's going to happen? I'm going to destroy the organic liquid. So I just wanted you to think about this from a critical perspective. All right, so challenges for air batteries, need for an overpotential to decompose lithium peroxide. Okay, stability could be improved using nanostructures. This is all pie in the sky. All right. On the other hand, lithium sulfur batteries are things that have been extremely well investigated. One of the things that you will find, yes, something else I wanted to talk to you about, homework. There are references, always there are references on the slides. I would suggest that if you are interested, if you want to learn more, which I hope you will go to the references and look them up. Here's what I encourage you to do. almost all of the references have introductions. A good introduction is one that gives you background information on the process that the paper is concerned with. It is that introduction and maybe some of the conclusions which are most valuable in understanding this area. As a consequence, I encourage you to go look at these when you feel that you don't know enough, because it's those introductions that, and even the abstract, which you can learn from easily without knowing all the details, okay? This is a easy way to learn, okay? So we are interested in making a lithium sulfur battery. And I mentioned, but I'll mention again, if you pay attention to the news on sources of organic fuels, there's in Canada, Athabasca tar sands, which are easily mined. And in Athabasca, in Saskatchewan, you can find pictures of mountains of sulfur, meaning it's something in search of, it's a problem in search of a solution. So sulfur is free, okay? So in principle, I have lithium metal, I have an electrolyte, and I have carbon plus sulfur. And I can now oxidize the lithium, and I can make, over on the cathode side, I can make a lithium sulfide of some sort. And in principle, the energy density is 2,600 watt hours per kilogram. We'll get to what that means, but it's quite high, okay? As I said, it's cheap, it's abundant, and you get 2 lithiums for 1 sulfur, so you can use 1 sulfur to accept 2 electrons, okay? The problem is cycling. This is where all of the issues are. And I'm pretty sure I said that one of the Nobel Prize winners, Stan Whittingham, has stated multiple times that he thinks lithium sulfur batteries are the real next generation. But he also says, unfortunately, in that same phrase, because there are a lot of issues that need to be resolved, okay? So this then is the typical challenge. So initially, 1630 is the theoretical energy density for a lithium battery. And immediately as you discharge it, you get a drop in voltage. Okay, what's happening in the first cycle? Flora? SEI formation, okay? So I'm forming an SEI, and there's another issue. The problem with using sulfur is that it doesn't conduct electricity. So now we always have to add carbon. That's okay. So it's going to turn out that the carbon is going to be an advantage at some point. So as we cycle it, we drop from 1630 down to 500. If we can keep 500 milliamp hours per gram, then we're very happy, because remember that graphite is 370 milliamp hours per gram. So we're still, and sulfur is just about as cheap as graphite. One of the problems with this process in a liquid electrolyte is that sulfur has many forms, okay? If you start with pure sulfide and you discharge and you lithiate the ring, okay, so it's crystalline, you lithiate the ring and the ring breaks down, well, opens and it breaks down to smaller chains, still smaller chains, and you get down here to the dilithium sulfide. And now when you charge, you go back, okay, and you don't get all of these intermediates. You probably do, but nobody says anything until you get to about the Li2S6. The problem is getting electrons in to oxidize the sulfur, okay, because it doesn't conduct. So the capacity should be above 1,000 and the voltage is about 2.5. It's not bad. But here are some issues. The sulfur reacts with lithium to form insoluble, unreactive lithium sulfides. So what happens is that the lithium sulfides are taken, or the lithium is taken out of the equation and the energy density drops. So of course, one goal is to prevent that from happening, okay? And it also siphons off lithium. So when that happens, you don't get the return on lithium, you get low efficiency, okay? And now you can also get disproportionation, which leads to self-discharge. And of course, the cycling is not reasonable for the reasons I just mentioned, okay? And let's see, the SEI is not stable. Okay, so it can continue to grow, which is part of the reason why the lithium is lost. It is possible to use lithium sulfide itself as a cathode, and people have studied this. It's still an issue because you have to use a high overpotential to begin delithiation because it doesn't conduct very easily, okay? So that's part of the problem. So among other things, these intermediate species are so diverse and they take up so much energy that they take up, how shall I put it? They are where you lose energy with time. And so the impedance changes, and that's part of the reason why the battery decays. I'm going to point out again that we will come back to this subject again in more detail. I will have a whole lecture on lithium sulfide batteries. All right, we'll do this way. Anybody have any questions? I wasn't sure I would get to the end. Okay, so now we'll talk about how lithium moves through liquids and solids and how it determines the behavior of batteries, okay, as a beginning, and then we're going to go into lithium movement in polymers, and then we're going to do it in gels and in ceramic materials, okay? So one of the reasons for doing the homework is to understand the driving force for, or the electrochemical driving force for a battery, okay? And electrochemical driving force begins with an understanding of the Gibbs free energy of formation of the materials that are assembled in part of the battery. So we're going to talk about that. We're going to talk about chemical potential, and we're going to talk about solvation and viscosity, solvation sphere, et cetera, as you can read here, okay? So as you now recognize, lithium ions don't move in and of themselves. They move in a solvation envelope or sphere. And so the free energy of movement is, and the diffusion of lithium is not just an ion, it's a cluster of solvent spheres. And when we get to be more sophisticated, we're going to find that lithium, in fact, can form clusters with anions, and it is sometimes the clusters themselves that move. And so our understanding of diffusion in a battery is different from a superficial understanding of diffusion, okay? So lithium ion conductivity, as annotated here, is something we're going to talk about only in aprotic solvents, meaning those without hydrogen in NH or OH or SH, okay? So we want to improve conductivity. We want to make the lithium ion be as isolated from other lithium ions as possible, okay? Because the bigger the cluster, the slower the diffusion, right? And so we want to create a salt that dissolves and ionizes essentially completely, so the lithium barely sees the counter ion, okay? So one way we do that is we increase the polarity of the solvent, which we would call the dielectric constant. We also want to increase, so we recognize that the lithium is solvated, but we want the minimum number of solvents around it that stabilize it, but don't cause a very big globule to move and diffuse. We want those solvent molecules to be very low, or very mobile, I should add, okay? So diffusion is d sub 0 at the radius of the solvating ion. Viscosity is that of the liquid, and this is Boltzmann constant, and d0 is diffusion in the perfect world. Okay. So you've seen these already, but let's just talk about these, because these are things that let's say that you have a project and you want to make a better battery, then knowing all of the issues that you have to deal with may help you to choose different materials. So remember that we have an operational window of about -40 to 60 degrees centigrade. So those also control the stability of the organics, or rather they set metrics for what is stable. So lithium ion diffusion rates in liquids are 10 to the -9th to 10 to the -11th meters squared per second. I don't suppose anybody offhand knows lithium ion diffusion rates in polymers or solids. So 10 to the -11th would be lovely in a solid, okay, but typically 10 to the -14th in polymers, sometimes even slower in solids. What does that do for us? It says if the residence time of the lithium is in an electrolyte is short, then you can still get a good flux of lithium, which is what you need for a good battery, okay? So that means, of course, that your electrolyte in a separator, really is what it amounts to, means that that system has to be very thin. Again, that also goes with the mandate for making a battery as dense as possible with the separator not counting in any conductivity whatsoever. Okay, so of course we want low flammability with our organics. So this is from a review article from 16 years ago. So this is not very exciting in terms of what we need to know for the future, but it's sort of like a way to give you a perspective. I think this was in a previous lecture, correct? See, one of the problems with also making video recordings is that some of these I've seen many times because they're in the video recordings too. All right, so this is dimethoxymethane, dimethoxyethane, diethoxy, all right, THF, methyl THF, et cetera. All right, so the molecular weights are shown here, but what we're really interested in is minus 40 to plus 60, right? So the melting temperatures are all well below minus 40, okay? The boiling point, this boiling point's too low. So it can never be used, except under pressure. Oh, gee, yeah, under pressure. So we don't want to do that. All right, so the viscosities though are very much lower. Water is 1, right? So we would like something at 0.4 to 0.5. And the dielectric constants are 3 to 7. They're not very good. All right, and we're going to end up spending time on real dielectrics that have much higher dielectric constant. Water, its dielectric constant is 80. That's why it's a wonderful solvent. That's why it's the elixir of life, if you like. Okay, so having said that, the freezing temperatures here are, I'm sorry, that's not the, what is that? I don't remember. It's okay, it's not that.
Flashpoint?
Yeah, I think that's it, flashpoint. Thank you. You're exactly right, flashpoint. All right, densities, that's more than water. So not what we want. We would like low densities. On the other hand, we want something that solvates very readily. Our goal is to find things that do better than this, but this is written in 2004, right? And this is, as far as I'm concerned, this is way out of date. You'll see that. I wanted, again, while I'm presenting lithium oxygen batteries and some of the issues with them and peroxides, you should see the other side. Okay, you should not be seeing everything that is all glamorous, okay? So this is the answer that is part of the homework, okay? There is the heat of formation or the free energy of formation of elements allows you to calculate in theory the energy difference, the free energy difference between two elements, group 1 and group 7, for example. And that would give you a theoretical driving force for a battery system, okay? And we can calculate the free energy from the free energy of reaction, which is the charge number of a mobile ion, usually 1, all right, +1, -1, all right, times Faraday's constant, and then the voltage, all right? So now we need to recognize, as I've said already, that the ions, the elements, don't move in a vacuum. They are solvated. When they are solvated, then we have something that is not the Gibbs free energy. We have something that is lower than the Gibbs free energy because it is the chemical potential that you can actually measure. All right, and that chemical potential will be determined by the solvation sphere, the temperatures, and other issues, okay, like the solvent. So the activity of all chemical species is really what affects this, and that is what I'm leading to, all right? So I think this is a good place to stop, and we will come back to this on Wednesday. Anybody have any questions? Again, the homework will be due Friday morning, okay? That'll give you enough time to work on it. Questions? No? Go get them. remember to clean your areas.